For solid objects, it is often more useful to consider the thermal expansion of only one of the object's dimensions, rather than the total change in the solid's volume. The change in any length dimension of an isotropic solid is equal to the coefficient of linear expansion, which is written as alpha subscript L, times the initial length dimension, times the change in temperature. The coefficient of linear expansion has the same units as the coefficient of volume expansion, namely Kelvin to the -1, or degrees Celsius to the -1. We will now find the relationship between the coefficient of linear expansion and the coefficient of volume expansion. Consider a box that is made of an isotropic material with a length L, a width W, and a height h. If the temperature of this box is increased by an amount equal to delta T, then based on the equation for linear expansion, the length of each of its sides will increase by an amount that is proportional to the initial length of that side. And based on the equation for volume expansion, the volume of the box will increase by an amount equal to delta V, which is proportional to the initial volume. The volume of the expanded box is equal to the initial volume, plus the volume increase due to expansion, or delta V. The volume of the expanded box can also be expressed as the multiplication of the values of its three expanded dimensions, its expanded length times its expanded width times its expanded height. We then replace delta L, delta W, and delta H by the coefficient of linear expansion, times the original length, times the change in temperature, and we get the shown expression. We can then simplify the equation by taking L, W and H out of their respective parentheses, and multiplying these three dimensions together, to get the initial volume V. We then divide through by the volume, and obtain the shown expression. By replacing the left-hand side by 1 plus delta V over V and expanding the cubic term, we get the shown equation, which can be simplified into this form by subtracting 1 from each side. We then recognize that since the linear thermal expansion coefficient is a small number, we can neglect the higher-order quadratic and cubic terms of alpha sub L. This leads to the shown expression, that states that the change in volume, divided by the original volume, is almost equal to 3 times the linear thermal expansion coefficient, times the change in temperature. Finally, by multiplying through by the original volume V, we get the shown equation, which by comparison to the original equation for volume expansion, is used to deduce that the coefficient of volume expansion is equal to 3 times the coefficient of linear expansion. We have proven in the previous section that for a box-shaped isotropic solid, the coefficient of volume expansion is equal to 3 times the coefficient of linear expansion. We can now apply this equation to any solid of arbitrary shape, like the one shown here, by recognizing that the geometry of any such solid can be approximated by a large number of box-shaped elements that are similar to the one described in the previous section. The bulb of a mercury glass thermometer is completely filled with 1 milliliter of mercury. It is connected to a narrow circular tube into which the mercury can expand. The diameter of the tube is equal to 0.1 millimeters. If the expansion of the glass is taken into consideration, what is the distance through which the mercury has to rise in the thermometer's tube to indicate an increase of 1 degree Celsius in the ambient temperature? In a previous example, we found the solution to this problem without taking into consideration the expansion of the glass. You may click on the shown link if you'd like to review that section. Now let's solve the problem, taking into account the expansion of glass. In the previous example, we found that the change in the volume of mercury is equal to 1.82 times 10 to the minus 10 meters cubed. We can use the same equation to calculate the volume expansion of the glass that makes up the bulb of the thermometer. Since the bulb is initially completely filled with mercury, its initial inside volume is equal to the volume of the mercury, and so we can rewrite the equation as shown. using a value of 27 times 10 to the minus 6 for the volumetric thermal expansion coefficient of ordinary glass, we get a volume expansion value of 0.27 times 10 to the minus 10 meters cubed. Since the expansion of the glass will reduce the volume of mercury that will go up into the tube, the net volume of mercury that goes into the tube is equal to the change in the volume of mercury due to thermal expansion, minus the change in the volume of the glass bulb, which gives 1.55 times 10 to the minus 10 meters cubed. We can then use the equation for linear expansion to get the amount of change in the diameter of the tube as a result of a temperature change of 1 degree Celsius. We substitute the coefficient of linear expansion of the glass by the coefficient of volume expansion of the glass divided by 3, and substitute the rest of the values into the equation. And we obtain a change in the diameter of 9 times 10 to the minus 10 meters, which is about 5 orders of magnitude smaller than the diameter of the tube, and hence can be neglected. Finally, we can find the change of height of the mercury within the tube, using an equation similar to the one we used in the previous example. Since we can neglect delta D, we can rewrite the equation as shown. Then we can substitute the net volume we just obtained, and we get a value of 1.97 centimeters for delta H. Compare that with our previous calculation of 2.32, which did not account for the expansion of the glass. That calculation was off by 17.8%. A useful application of linear thermal expansion is the bimetallic strip. It is made up of two bonded dissimilar metal strips that have different coefficients of thermal expansion. For the shown bimetallic strip, the coefficient of linear expansion of the top strip is larger than the coefficient of linear expansion of the bottom strip. When the temperature of the strip is increased, the two metals expand by different amounts, due to their different coefficients of thermal expansion. If the two strips were not bonded together, this would simply result in the side of the strip that has the higher coefficient of thermal expansion becoming longer. But in the bimetallic strip, since the two strips are bonded together, the strip curves towards the side with the lower coefficient of thermal expansion. The mechanical displacement of the bimetallic strip, which is a function of temperature, has many applications, as we can see from the shown movie. If the strip is coiled around the metal side that has the higher coefficient of thermal expansion, then heating the strip will tend to uncoil it. The resulting circular motion of a plate that is attached to the end of the bimetallic strip can be used to move the needle of an analog thermometer. Another application of the bimetallic strip is as a temperature-activated switch that can connect or disconnect an electric circuit at a predetermined temperature. As can be seen from the shown graph, the thermal expansion coefficient of liquid water varies greatly with temperature. At a temperature of 4 degrees Celsius, the coefficient of volume expansion of water is equal to 0. And between 0 and 4 degrees Celsius, the coefficient of volume expansion of water is actually negative. This means that within this temperature range, water expands as the temperature decreases.